Welcome to this second half of today's lecture. Remember that we are studying integral extensions. So now I want to switch on to the study of prime ideals under integral extensions. So we are in the following situation. So let A be our base ring and B be an algebra with structure homomorphism phi from A to B. And then remember we have defined when is B integral over A, B integral over A. That means every element of B satisfies the monic polynomial over A. But then this is also said, sometimes also say, or phi is integral homomorphism, phi is integral over A. This is just language. And in this study we may also assume actually A is contained in B. So this is by replacing A by its image in B. So this is a ring extension. That simply means that there is a inclusion ring homomorphism from A to B. And then we say it is integral. That means every element here x is integral over A. Every. That is our assumption. Now remember, this any ring homomorphism will induce a map on the spectrum. So then we will have a map spec, if you call this as inclusion map, spec of B to spec of A. This is a natural map. This remember we have called it I star, which is any prime ideal P prime. Where does it go? Just pull it back, contraction, that is I inverse of P prime. This is also denoted by P prime intersection A. This is again by abuse of notation, but this makes sense in this particular case. I would like to keep actually general phi, that does not matter. So we want to study this map. Now this map is a continuous map. This is a continuous map we have seen. This is continuous with respect to the Zariski topologies, on spec A and spec B. So that simply means that if I have, so one way to check continuity is check that inverse image of a closed set is a closed set. And we know closed sets in a Zariski topology on the spectrum A is this notation V of an ideal A. And then what is the inverse image? So iota star inverse of this set is precisely V of whom? V of the extended ideal, V of AB. This is what we have checked earlier lectures. So its continuous is we have checked. Now I am addressing to the question more. Now we have, this is so far for arbitrary ring extension or arbitrary ring homomorphism. Now we have extra condition here, integral. So what will this extra integralness will reflect some properties of this I star map. For example, is it surjective? can you describe the fibers, and is it a closed map or is it an open map, and so on, such properties. So these are the topological properties. So we are trying to convert the algebraic property of integralness into a topological property. So this is what I want to study. So for this study, first I will do arbitrary ideals. What happened to the arbitrary ideals? What can you say? Little more. So I want to prove a proposition first. So proposition. This proposition is very important in proving the properties of the spec map. So proposition, let A contained in B be an integral extension of integral domain with of integral domains. That means A and B are integral domains and this is an integral extension. That means every element of B is integral over A, means it satisfies a monic polynomial with coefficients in A. Alright, then one and so, and let me say if B is an ideal in B, use our notation IB, B is an ideal in B non-zero, then the contraction of B to A, B intersection A, this is a contraction. If you want, this is iota map, I map, but this is clear. So this is also non-zero. 2. If A is a field, then B is also field. And 3, actually I should write in 2 only, if and only if I want to write. So let us write that more general statement. A is a field if and only if B is a field. Alright, so proof is very simple. I want to check that this ideal contraction of B is non-zero, and what we have given, ideal B is non-zero. So start with a non-zero element there. So let B in B, ideal B be non-zero. There is such an element because the ideal B is given to be non-zero. And now this extension is given to be integral. That means in particular this element B, which was in ideal B, which is also an element in capital B, which should satisfy an integral equation over A, and B power n plus a n minus 1 B power n minus 1 etc. B A1 B plus A0 equal to 0 be an integral equation of small b over A. So that simply means these A0 to An minus 1, they are elements in the ring A. So this is a monic polynomial with coefficients in A and B satisfies that. Now what? Then it is very clear. Then what do you get? I choose the smallest one, B the integral equation of B over A of the smallest degree. N. This makes sense because among the equations I will choose the smallest degree equation because the n is varying in the natural numbers, and so there is one equation, so say it is non-empty, so I choose the smallest n. Now if it is the smallest degree, this equation I rewrite it. So I claim that then A naught has to be non-zero, because if A naught is non-zero, if A naught is 0, then this equation will have B in common, and B is a non-zero element in an integral domain, so I will cancel it, and therefore I get a smaller degree integral equation for B. So A naught is non-zero, and where is this A naught? And A naught will it belongs to A, that is because it is a coefficient. On the other hand, it belongs to the ideal it is a multiple of B, it is a multiple of B. Therefore it is in the ideal B, because B is in B, therefore any multiple of B is also there. So this is in A intersection B. Since A naught equal to minus B times whatever remaining part, this is in B. So one is easy. So this was the proof of 1. 2, I want to prove that A is a field if and only B is a field. So first I will prove this way. If A is a field, then the upper bigger ring is also field, provided it is integral. Alright, so start with any element in the ring B. It is a domain, so let B be in B and assume B is non-zero. And what do you want to prove? Want to prove B belongs to B cross. That means it is a unit in B. Then we would have proved that every non-zero element is a unit, therefore it is a field. Alright, so how do you prove that? Now let us take the ideal B. B is an ideal generated by B. This is an ideal in B, and it is a non-zero ideal. This is a non-zero ideal because the non-zero element belongs there. And what does 1 say? 1 says that if I take the contraction of this ideal B to A, then it becomes a non-zero ideal. Then B intersection A is non-zero ideal. It is an ideal in B, ideal in A, and it is a non-zero ideal. But A is a field given, A is a field given. So what are the ideals in the field? Either 0 or whole thing. So that will imply B intersection A equal to A, since A is a field. But in particular 1 will belong there. So in particular 1 will belong to right side, therefore it belongs to the left side. That means it belongs to 1 which is 1A, which belongs to A, which is B intersection A. So 1A belongs to the ideal B, but 1A is same thing as 1B because A is a subring of B. So that implies in particular that B is a unit ideal in capital B, but this B is generated by B, therefore B has to be unit. So B belongs to B cross. So we have proved that B is a field. So this proves that B is a field. Now we are proving this way. So suppose that B is a field and A is an arbitrary element in A is a non-zero element. And what is to prove? Want to prove this element A belongs to the units. This is what we want to do. All right. Now here A is here, B is bigger ring, A is an element here, A is a non-zero element here, and this is a field. So this is a non-zero element in the field B. So A inverse definitely belongs to B. And actually we want to prove that A inverse belongs to A. Alright, A inverse is an element in B, but B is integral over A. So A inverse will satisfy a monic polynomial with coefficients in A. So therefore we have an integral equation. So that is A power minus n plus A n minus 1 A power minus n plus 1 plus A1 minus 1 plus A0 equal to 0, where this A0 to An minus 1 they are elements in the ring A. These are the powers of minus 1. You see, minus 1 minus A power minus 1 power n minus 1 and so on. No? Alright, so we have such an integral equation. Now you can multiply this equation by A power n on both sides. So what do you get? You get here multiplying by A power n we get. So here it will be 1, here it will be plus an minus 1, and A power n I multiplied, so it will be A plus so on. So powers of A will keep increasing now. A1 power A power n minus 1 plus A0 times A power n, this is 0. But now it is obvious what is the inverse of A. Then that implies minus, I keep 1 on this side and shift everybody the other side. So 1 will be equal to, and I take common A from there, A times minus An minus 1 minus An minus 2A minus A1 A power n minus 2 plus A0 A power n minus 1. So this is obviously an element in the ring A, and it is an inverse of A. So that implies A inverse belongs to the ring A. So that proves that it is, so therefore we have proved that A is a field. So this is very useful for studying prime ideals because, or maximal ideals, because you want to check some ideal is prime, then you have to check the residue class ring is a integral domain. If you want to check some ideal is maximal, that is equivalent to checking the residue class ring is a field. Alright, so let us now go to the study of prime ideals and maximal ideals. Alright, so this is a very important theorem. So these theorems, the following, we will prove following 3 assertions, following 3 theorems. Maybe I will not be able to finish all the proofs today, but we will carry over to the next lecture. Are known as, are important, and are known as Cohen-Seidenberg theorems. So both these Cohen and Seidenberg, they are students of Zariski. In fact, Cohen was the youngest student of Zariski, who unfortunately died very young. Alright, so what are the theorems? So, our assumption is always let A contained in B be an integral extension of rings. Then one, let P prime be an ideal in prime ideal in B, and P be the contraction of P prime, A intersection P prime. This is obviously a prime ideal, that is no big deal, because contraction of a prime ideal is always a prime ideal. In fact, so this is because you see here we can draw a little diagram, A contained in B, and then this P prime is given there. So, A B to B by P prime, this is an integral domain that is given to us. And then when you contract, what happens? When you contract A by P prime intersection A, this map induced by this will be also an inclusion map. That is very simple. If somebody goes to 0 here, it will go to 0 here, and you can check. So, this is inclusion map. So, this is integral domain, therefore, this will be integral domain. So, this is P. So, because this is a domain, that will imply A by P is also domain, and that will mean that the contraction ideal P is a prime ideal in A. So, that is the proof of contraction of a prime ideal is a prime ideal, no big deal. Moreover, P prime belongs to SPMB, that is P prime is maximal if and only if P, which is contraction of P, is a maximal ideal in B, a maximal ideal in A. You know, this was one of the difficulty when we were studying arbitrary ring extensions. Contraction of a maximal ideal may not be maximal, but it was true for finite type algebras over a field. But in integral extension also it is true that contraction of a maximal is maximal. Proof is very simple. So, let me finish the proof itself. So, proof. So, what happens again? So, again draw a diagram A to B, this was a given integral extension. Then we have A by P here, this P is the contraction, that to B by P prime. This is the residue maps, and this is also inclusion map, because we have gone mod the kernel of this. So, this is also inclusion map, and I claim this is also integral. This integral implies this residue map is also integral, because if I take any element B bar here, that will coming from some B here, because this map is surjective, and this B will satisfy integral equation over A. Now, take that integral equation and read mod, and then you will get coefficients here, read mod P, then you will get back. So, this is also integral. Now, what is the advantage? Now, this is a domain we know, therefore, this is also domain we know, and integral. Therefore, if P were maximal, if P prime were maximal, that means this is a field. Then by the earlier lemma proposition, then this will also be a field. Conversely, if this is a field, this is also a field. Okay. So, I will write it down. Now, the assertion follows immediately from two of the above proposition. Namely, P is maximal, P prime is maximal in B if and only if P is maximal in A, where P is the contraction. All right. So this means what? This means the original map is we have A to B. This is our original ring homomorphism which we are assuming integral. Then we have a map from spec B to spec A. This is I star, this is I, and we have checked that under this there is a SPMB here, there is a SPMA here, this is a subset here, this is a subset here. Under this subset will be mapped onto this subset. So that means I star will induce this map, maximal spectrum on the maximal spectrum. This is very useful. Now the next one, the second statement is this map I star, this is from spec B to spec A, is surjective. What does that mean? That is, for every P in the spectrum of A, there exist P prime in spec B with iota star of P prime is P. So this is by definition P prime intersection A. So that means there is at least one prime ideal P prime in B which will lie over P. So this is called lying over theorem. This theorem is called lying over theorem. I will draw a diagram on the next page that will explain why is it called lying over theorem. All right. So what is it? So let us draw a diagram. All right. So we have here B and here we have A, and this is an integral extension, and we have given P here. This is a prime ideal here. This is a prime ideal here, spec A. Then what do the theorem says? There exists P prime which is a prime ideal here. This is in spec B, such that when I contract it, it goes to P. So there exists a prime ideal above. When I contract it to the ring A, it becomes precisely P. That is why here we say the language is used is P prime lies over P. In the spec map, that means P prime is mapped onto B under iota star to P. This is a surjectivity. All right. So I will stop here and we will prove the statement in the next lecture. Moreover, also we will discuss that how many can do, how many will lie over. how many prime ideals will lie over the same given prime ideal. That means we will describe the fiber. So what happens to the fiber over P? So that is the next goal, and then these lying over theorems are these Cohen-Seidenberg theorems are very important, especially to prove what is dimension. Dimension. How do you compare dimensions of the rings under integral extensions? When I say dimension means screw dimension. Again, this concept of dimension is very important, but I think we will not be able to touch in this course. But I have proved starting with dimension, I have proved many things in the next level commutative algebra course, which was in 2018 IIT NPTEL course, which was from IIT Bombay. So with this I will stop here, and we will continue this study in the next lecture. Thank you.